Okay, Chapter 7, Section 2, Partial Derivatives. Okay, so in this section, we're going to talk about how to take derivatives of multivariable functions. But before we do that, let's do a real quick recap of what it means to take a derivative in a single variable function. Okay, so here is our definition of a derivative back from Chapter 2. If y equals to f of x is a function that's given, we define the derivative of f at x, denoted by f prime of x, by f prime of x equals to the limit as h goes to 0 of the differential f of x plus h minus f of x all over h, if the limit exists. So if f prime of x exists for each x in an open interval from a to b, then f is said to be differentiable over the set a to b. Okay, so here's our formal definition back from chapter 2. And let's do a graph to refresh our memories of what this actually means. So I'm going to use Desmos. Okay, so here in desmos.com, let's say that I'm working with this function here in blue. Let's see the equation. That's this equation right here. F of x equals to f of x equals to x cubed minus 3x squared. Just a random function I created. So that's this one right there. Okay, so now what we're interested in is figuring out the instantaneous rate of change of this function at a particular point. So for example, let's say we're interested in this purple point right here, right, at various points along the function, right, given some input value. So like right now it's at negative 1.5. Given some input value, there's an output value of negative 10.157, right, according to this function here. And so as that point travels along the function, we want to know the instantaneous rate of change. So not only do we want to know the input and output of that point, but we want to know where is it heading next. So right now the input is 3.4, the output is 5.2, but where is it going? I could see that it's going that way, right? Because I can see the whole graph. But I want a numerical description of where it's going next. On the other hand, say over here, the input is 0.85, the output is negative 1.5, but additional information is that it's on its way down, right? So that's the instantaneous rate of change. So how do we get that? So this is what we're after. Let me just graph it. We want this, the tangent line. This red one is the tangent line. So as the purple point travels along the function, we can see that tangent line change. So see at this point right here, we know the input, we know the output of the function, but then we have some information. We know that it's also on its way up, right? The steepness of this red line tells us the instantaneous rate of change of the purple point at that value. So as that purple point travels, we see that the steepness of that tangent line, the slope of that tangent line, is changing. So we start out at really big positive, right? A little stick person walking on this from left to right would be going uphill. So that's a big positive slope, smaller positive slope, smaller positive, still positive though. And then it gets really small positive, really small positives until it reaches zero, right? Right there, zero slope. And then becomes a small negative, then a bigger negative, bigger negative, bigger negative, bigger negative slope, bigger negative slope, until it reaches its maximum negative slope, and then becomes a smaller negative slope, still negative, but smaller negative until again it reaches zero right there. And then we get a small positive slope. Notice that the output of the function is still negative, but the slope is now a small positive slope of the tangent line, and then bigger and 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 bigger. Okay, now how did we achieve this, right? That's where that definition comes in. So let me zoom into this. I'm going to change the dimensions of this. Let's go to like -3 to +3 kind of space here. -3 to +3, just to kind of zoom into there. Okay, let's say we hold this steady right there. The input value is 1. The output value is -2. Okay, and we're interested in figuring out the slope of that tangent line there, and once you find the slope of the tangent line and you have a point, then you can come up with the equation of that red line, right? So the way we do this is to think of another point on the function, right? Because in order for us to find the equation of a line, we need 2 points. So we come up with another point. So let's graph another point. How about that point right here? And let's put it over here. So let's put it up here. Okay, so what I've done is I've taken this point right here, 1 comma negative 2, and then I've gone a distance h along the horizontal axes. And at the moment, h is 5. So then 1 plus 5 lands at 6. And then that becomes the new input value to the function. So now I evaluate my function at f of a plus h, which gives me the output value. So I have this point, right? So the point is that we have 2 points on our function, this point and this point. And now that we have 2 points, we can come up with the equation of the line. So we can draw this line, right? This green line right there. So at the moment, the slope of the green line is very far from the slope of the red line, of course, but it would serve as like an initial approximation. Obviously, a terrible, terrible approximation. And if you recall from chapter 2, then what we do is that we let h get smaller and smaller and smaller, right? As h becomes closer and closer and closer to 0, as this guy moves closer and closer and closer to 0, then this is held steady, and then over here, this input value begins to get closer and closer and closer. In fact, let me graph that point as well. So let's graph the point h comma 0. Oops, a plus h comma 0. Okay, so this is the input value into our function as h gets closer and closer to 0. So let's get back over here to h equaling to 5, right there. When h equals to 5, the input value is 6, and then we evaluate the function at 6, which gives us, at this point, 108. Okay, and so as h gets closer and closer and closer and closer to 0, then this red dot gets closer and closer to the purple dot. Well, the input value here gets closer and closer to 1. And as it gets closer and closer and closer to 1, we can see that this green secant line, connecting the purple point and this green point, the slope of that line is going to get closer and closer and closer to this red one. Again, let me zoom into here to get it to look a little nicer, like that. Okay, so then as h gets even closer, you see that it starts to become a better and better approximation. Right around that point, you start to think, okay, maybe the slope of the green line is starting to seem close to the slope of the red dotted line, right? And at this point, we're holding h to be 0.7. We can get even closer, right? H can get really, really, really close to 0 as possible. Here it is at 0.4. And you can already start to tell that the slope of that green line is indeed becoming a pretty good approximation of the slope of the red line. Okay, so hopefully that sounds familiar. Let me draw up some of this. All right, so let's bring it back to our definition of a derivative. So remember that I had defined this as function f of x equals to x cubed minus 3x squared. That's just the random function I chose. And we were looking at a derivative here at a equals to 1. A equals to 1. And then if we plug it into our function, f of 1 equals to 1 cubed minus 3 times 1, which gives us a negative 2. So we were looking at the point 1 comma negative 2, right? That's this point right here. So here this is where a equals to 1. And then we're going to let h be the distance between the input value a all the way out to the point a plus h. So all the way out to the point a plus h. So this distance right here is h, which makes this the point a plus h. Good. Okay, so then this point right here, putting it in terms of a, this is the point a comma f of a. That's that point. When a is 1, f of 1 is equal to -2. And then this point right here traces down to this point here. Okay, so then this point then becomes the input value a plus h, comma, f of a plus h. Good. That's this point right here. Okay, and now if we are interested in finding this equation right here, the secant that connects this point and this point, we would need the slope, m equals 2. And so the slope would be equal to f of a plus h minus f of a divided by a plus h minus a. In the denominator, the a's cancel, giving us a slope of f of a plus h minus f of a divided by just h. Okay, so this is the slope of this green line, the secant line. The slope of a line that is created by using these 2 points, right? So if a is given as a constant in this example, a, right? A equals to 1. So if a equals 1, and then h is held to some value as well. Like in here, I could see it's 1.394, right? So h equals to 1.394. Then adding 1 plus 1.394 gets you to this input value. That leads to this value there, and then we can create that. So if we hold a and h to be a specific constant, we can plug it into this little formula and then gives you the slope. Okay, well, the point is that we're going to hold this constant. The a is going to be held constant because we're interested at finding the tangent line to this one here. Right? We're interested in finding the slope of the red tangent line at this point. So we're going to hold the a equals to 1 constant, and then we're going to figure out or kind of examine what happens as h gets closer and closer to 0, right? As h approaches to 0, and for the simplicity of my picture here, let's just say that it approaches it from the right-hand side, so it's always positive. And so that means that this dot right here is going to get closer and closer and closer and closer to that point there. And as that happens, its corresponding value along the function is going to travel along the function and get closer and closer and closer and closer to this dot, right? So that at some point when it's really, really close, we can see that the line that connects the purple and the green, as the green travels along this function, and as the green travels along this way, along the function, this dot is traveling along them that way, right? The input value is getting closer to that one. The function value is traveling this way. At some point, and this red dot, find the secant line that connects them. The slope of that line will be a really good approximation to the slope of the tangent line. At any specific point, they're not equal to each other. But if we think about what happens as they travel to infinity, at infinity, we say that the result of this secant will give you the slope of the line tangent at that point, right? And that leads to this. So then the limit, we want to consider the limit as h approaches to 0 of this f of a plus h minus f of a all over h. This is the derivative of a function evaluated at a. F prime of a is defined to be this, the limit as h approaches to 0 of this. Good. Of course, algebra loves x, so we want to rewrite it back in x. This is where x equals to a, right? That's this function here. The input value along the horizontal axis x is equal to a. But, you know, there's nothing special about the letter a. We could say for any for any variable. So we can just rewrite this back into x, right? So this is how you normally see it. F prime of x is equal to the limit as h approaches to 0 of f of x plus h minus f of x all over h. And that leads us back to our definition. So let's take a look at that again. There. So there's that formal definition of a derivative. Okay, so hopefully that sounds familiar. Of course, we developed this derivative by the limit definition, and finding those derivatives was always a lot of work, right? So then we developed a bunch of shortcuts that helped us find derivatives faster. We briefly kind of proved why those shortcuts must work, but in a more rigorous class, you spend a lot of time really proving and showing that those little shortcuts really do give you the correct answer. But in this class, we didn't spend that much time on that. We just focused on figuring out those little shortcuts and then applying and using those little shortcuts, the laws of derivatives, to find the derivatives of really complicated functions. Finding those derivatives without the shortcuts would be, really, really tough. Okay, so hopefully this was a nice refresher of what a derivative is, right? It's the slope of the line which is tangent to a function at a point, right? It is used to describe the instantaneous rate of change of a function. Okay, so we want to take this definition of derivative and then extend it out to a function in more than one variable. We'll start with just two. In fact, we're only going to cover two in this section, I believe. And then usually we like to use the letters x and y to be our two input variables, and then the letter z to represent the output variable as a result of using those two input values, x and y. Okay, so let's extend this derivative definition to two variable functions. Okay, so in general, if z is equal to f of x comma y, then the partial derivative of f with respect to x, denoted as dz dx, or f sub x, or f sub x of x comma y, is defined to be dz dx equals to the limit as h approaches to 0 of f of x plus h comma y minus f of x comma y all over h, provided the limit exists. Okay, so this should look very, very similar to the derivative equation we just saw. The only distinction here is we've got to pay attention to the fact that there are two input variables, x and y, and one output variable, z. So what we're going to do is hold y to be some constant, hold x to be some constant. We're interested in figuring out the instantaneous rate of change of that point in that three-dimensional image in the x-axis direction. Hopefully that will make a little bit more sense when I describe it with a graph. So in a little bit, we'll get into a graph and a picture, and we'll get a better sense of what that means, I hope. And then a similar definition is given for the derivative of the function z with respect to y. So the partial derivative of f with respect to y, denoted as dz dy, f of y or f sub y or f sub y of x of y, is defined by dz dy equals to the limit as k goes to 0 of f of x comma y plus k minus f of x y all over k, right? So let's limit it down, right? So this is in general for any point x comma y, but let's limit it down like we did before with just some a comma b. So let's say that, just as a quick little description of what is happening here, we have the x comma y axes like this. And so let's say that we have some point along the x-axis, x equals to a, so here's a, and then here's some other point b, so that they travel along the base of this thing, so along the floor, and we arrive at some point a comma B. This becomes the input value, and it is plugged into our f function, and it will travel to some value that's the output. So it'll be some value sort of above or below that point, right? It's a 3D image. So if, let's say that we have some function in green up here. So assuming that this green is like this little carpet thing flowing over the top, where the outputs of this green one are the z values, right? This is f of x comma y. And so this point here travels up, right? Once we plug in a and b into our function, it travels up until it slams into that floating carpet above, which is the output functions. So let's say that it hits right there. Right, so there's some point above this one on the green. Maybe I should put it green, right? I don't know, let's do it green. Some green dot on that green carpet that represents the point f of a comma b. Right, at least the height of it is equal to that. Good. And we're interested in figuring out the instantaneous rate of change of that point. Well, as we can see, it's a 3D image. So if you're standing on here, if you have like a little stick man right here, just kind of standing there, and you're like, okay, what's the instantaneous rate of change if you take one tiny, teeny, tiny little step? What's the steepness of that? Are you going up? Are you going down? What's happening along this three-dimensional image? Well, it will vary, right? It's kind of hard to see here, but this is, this could have dips and valleys. This isn't necessarily like a flat space. I just can't draw it any better. I'll use technology in a minute and it'll look better. But I mean, over here there could be bumps and valleys along this carpet function value. So at that point, maybe if you walk this way, you're walking down. Maybe this function kind of goes like that there. If you're walking that way, maybe it goes kind of flat that way, or maybe it goes up if you walk back that way. So not only would you have to ask what's the instantaneous rate of change, but you also have to add a direction to it. That's what we have to do now. So that's why we have two that we're working with. This is the instantaneous rate of change if you were standing on the point a comma b and you wanted to walk in the x-axis direction. So coming back this way, let's say that it looked like this. So if you're facing the x-axis, if you're going to hold the y equals to b constant, then as x approaches to a, right, if we kind of consider this description over here, we could think about some other point that is along the x-axis. So let's put it back over here. So let's say we have some a plus h value there, so that this is h. Good. So if we hold this to be constant, the b is constant, the a is constant, and the only thing that's changing is the h, then the values along the floor of this function will be anything over here. Let me erase this. Okay, so there'll be some values there, right? And so as h approaches to a, as h gets closer and closer to 0, there will be some corresponding point here that will get closer and closer and closer to this point, right? The input value will get closer and closer to that one. And as that happens, the corresponding values along the function will get closer and closer and closer. Maybe it starts way down here, corresponding to this point. And then this point here corresponds to a point there. And then as you get closer, it corresponds to a point there, right? So we get these points, which are getting closer and closer to that point there. And again, just like before, if we think about the secant line that connects the point we're interested in to these other points generated by evaluating different points, right? then we look at that, the slope of those secant lines, and then the limit as those points get closer and closer is what we're interested in. This is kind of an ugly graph. I'm not really great at drawing, so hopefully you kind of got what we wanted. But if not, okay, let me see if I can insert some green lines here. Okay, so here is this line. So we want to think about the slope that connects these 2 points. And then as it gets closer and closer and closer, we want to do it again. Let's insert it again. Now we want to insert a line that connects this point and say that point right there. Okay, let's make it thicker. Right, so now it's a point connecting the one we're interested in. We're holding that constant. And so initially we are thinking about the point that connects this one, and that's this one. Let's call this M, let's call that M sub 1. The slope of the secant line that connects the point of interest and this point, good, which is a point determined by evaluating our function at the input value. Let's go here. This point right there is determined by plugging in this point here in the floor of our 3D function, which is equal to the point A plus H, comma B, right? That's this point here. And then as I evaluated, that means that this point here will be the point F of A plus H. Right, we evaluate our function at A plus H. Oops, forgot the B, comma B. That's this point right here. And we find that secant line. And then we let this get closer and closer and closer to this point. And as we do, then the resulting points traveling in this 3D function will get closer and closer to the target point. And we're interested in the tangent line at that point. Okay, so the tangent line might be something that ultimately might just look like that. Like that red one. Good. Okay, very similar to our definition of a derivative using a single input variable. So here with 2 input variables, that's what we get. Later on, I'll use technology to describe this whole thing, and the picture will look a little bit better, I hope. In the meantime, let's just dive into how you find these derivatives with a specific point. So let's look at an example. Okay, so let's say that we're given the function f of x comma y equals to 2x cubed plus 3x squared y plus y squared plus 2. Okay, so this is a function in 2 input variables. You plug them into here, and then you get your output value z, right? So remember, this is also z equals to this function. Okay, so let's say that we're asked to find this. Find f sub x at 1 comma negative 2. Okay, so this is the derivative with respect to x of this function evaluated at the point 1 comma negative 2. Okay, so let's just set up the limit definition of a derivative, and we'll take it from there. So this is equivalent to the limit as h goes to 0, and we're going to have f of 1 plus h comma negative 2 minus f of 1 comma negative 2 divided by h, right? So the limit as h approaches to 0 here will give us our derivative with respect to x. Okay, well, just like before, this is not so fun. We want to really go to our shortcuts to finding these derivatives, and it actually works out to be quite nice in this case. So let's find the actual derivative, right? This is not really how we're going to find derivatives. I just wanted to set up the limit definition of derivatives but how do we actually find it? So let's come back over here. I'm going to find it in general, right? So let's just pause for a second and go back to the general function. So what I'm going to do is I'm going to go through here and I'm going to find the derivative with respect to x on all of this. Remember, this notation is equivalent to a variety of notations. This is equivalent to saying find dz dx, which is the same thing as saying find d dx of the function z, which is the same thing as saying find the derivative with respect to x on f of x comma y. Right? All these things mean the same thing. And in particular, I'm going to adopt this notation style. It's the derivative with respect to x of, and then instead of writing f of x comma y, I'm going to write this guy, which is going to be 2x cubed plus 3x squared y plus y squared plus 2. The derivative of this function with respect to x. Now, when I actually take the derivative, we're going to follow all the exact same rules as before of finding derivatives. The only thing we have to keep in mind is, well, what do we do when we run into a y? Right? So for the purposes of finding a derivative with respect to x, the other letters are treated as constants. So even though it has a y there, think of just putting some number there and then what would happen. So think, let me put it over here on the side here, think derivative with respect to x, 2x cubed plus 3x squared, let's put that there as a blank, plus blank squared plus 2. And let's, instead of a y, just your favorite number, how about 7? I don't know, let's say that the y is 7. It doesn't matter. Nothing special about the number 7. I'm just pointing out that it's just some constant. If we were taking the derivative of this function, then the derivative of the first part here, right? Well, actually, let's just take a couple steps here. This is equivalent to the derivative of the 2x cubed plus the derivative with respect to x of the 3x squared times another 7 plus the derivative with respect to x on the 7 squared plus the derivative with respect to x on the 2. Okay, and so now the derivative with respect to x on this first term is going to be 6x squared plus, well, 3 and 7, that's just really 21. This is equivalent to just rewriting this as 21x squared. 21x squared. And the derivative of 21x squared would be 42x. Right? So this is 42x, or just kind of copying it down. Oops, just kind of copying it down. It's going to be the 21, right? And then we multiply it times 2, x to the power of 1. This 2 comes from bringing that exponent down in front as a linear factor. Good. And then these two, well, the derivative of a constant is always 0. So we end up with 0 plus 0. Okay, well, we want to follow the same process over here, except we don't want to rewrite the y as a 7, but we want to think of it as a constant. So whenever you see it, think of 7, or think of some constant. So this becomes the derivative with respect to x on the 2x cubed plus the derivative with respect to x on the 3x squared y plus the derivative with respect to x on y squared plus the derivative with respect to x on the 2. Derivative with respect to x on that 2. Okay, so we can see that for this first term, we're going to get this, 6x squared. Then here, we're going to bring the 2 out in front, so we'll get 2 times 3 times y, right, where y is some constant. Good. So let me go ahead and write that down. Let me erase these guys. So this is going to become 6x squared plus 3 times 2 times y, x to the power of 1. Right, where I've taken this 2 comes from the fact that that used to be a 2 in the exponent. We bring the 2 out in front like a factor, and then we subtract 1 from the exponent. right? That was our power rule from back in chapter 2. And then we end up with a plus. And, well, this is a constant, right? Don't fall under the idea, this is a mistake, people do this. We don't want to do that because this is derivative with respect to x on a function y, where y is another independent variable that is being held as a constant. So this is equal to 0. Right? You don't want to do that. This is going to become 0 from here. This is a 0. And so is this. That's the derivative of another constant. So it's 0 plus 0, or just gets ignored. So then our answer is really just going to be 6x squared plus 6yx. Here, this is f sub x of x comma y. Good. So this is the derivative of our function with respect to x. And now that we have this function, we can go back to the point 1 comma negative 2 and evaluate this function at those results. So now f sub x at 1 comma negative 2 is equivalent to 6 is equivalent to is equivalent to 6 blank squared plus 6 blank times blank, and the x value is a 1, so we're going to put a 1 there and a 1 here, and the y value is a negative 2, so we're going to put a minus 2 right there. So f sub x of 1 comma negative 2 is equal to 6 minus 12, or f sub x is equal to 1 comma negative 2 equals to negative 6. Okay, so now let's do the exact same thing, but now for y. So let's see how that changes. Erase this here. And we'll say now we want to find f sub y of 1 comma negative 2, setting up that limit, the limit as, and let's use the letter k, approaches to 0. Nothing special about the letter h or the letter k, it's just common variables used. And so this time it would be f of 1 comma negative 2 plus k minus f of 1 comma negative 2 all over k. As k goes to 0, notice that the 1 is now constant, and minus 2 plus k becomes the new input value as k approaches to 0. And then we have our definition of a derivative. Just like before, these aren't fun, so we want to work with our shortcuts. And our shortcuts that we learned before still apply here. So this f sub y evaluated at x comma y, right? So this is just a generic derivative, not at a particular point. We're going to find it at a generic derivative and then evaluate it at the point 1 comma negative 2, just like before. So this notation is the same thing as a variety of different notation styles. We can also say that this is dz dy, again, where z equals this function, right? Z equals that function, which is the same thing as ddy of the function z, which is the same thing as ddy of this function, ddy of the function 2x cubed plus 3x squared y plus y squared plus 2. Okay, so just like before, we can separate this into ddy of 2x cubed plus, and then ddy of 3x squared y plus dy of y squared plus ddy of 2. Okay, and so remember that if we're taking a derivative with respect to y and x is another constant, we're treating x, and x is another variable, independent variable, we're going to let x be a constant in our heads as we're trying to find the derivative of this. So do not make the mistake of thinking that this is equals to 6x squared. That would be correct if it was the derivative with respect to x, but it's the derivative with respect to y. So x is considered to be some constant. Again, think of x being a 7 or something. 7 cubed times 2 is just some number. And the derivative of some number with respect to y is just going to be 0. So this becomes 0 plus. The x squared, again, is just some constant. The only variable, independent variable here is the y. So this becomes plus 3x squared, right? If this was just like 3y, its derivative would be just 3. So 3x squared y becomes just 3x squared plus 2y to the power of 1 from here. And again, the derivative of that guy is just going to be 0. Good. So we end up with a derivative of 3x squared plus 2y. Right, this is f sub y of x comma y. The derivative of our function with respect to y is this one. Good. And so tying it back into the point 1 comma negative 2, we have that f sub y of 1 comma negative 2 is really equal to 3 times blank squared plus 2 times blank, where the x was a 1, so 1 goes there, and the y was a negative 2, so that goes there. So f sub y of 1 comma negative 2 is equal to 3 minus 4, which is going to be negative 1. All right, let's organize all of this. Let me erase the definition of limits. Okay, so organizing this better, we found that f sub x, the derivative with respect to x on the function x comma y. Okay, as we go through this here, we see that this was equal to 6x squared plus 6yx, right? 3 times 2 minus 1 gives you this term. And then bringing down the 2 gives you 6 x to the first power, and the y is some constant we attach, so 6yx squared plus, and then these two are zeros, so that's the end of it. And then if we evaluate this derivative, f sub x, at 1 comma negative 2, we found that we got a negative 6. Likewise, we had f sub y of x comma y. Now the derivative with respect to y. First term is 0, since there's no y's in there. Second term is just y to the first power, so then that just turns into 3x squared plus 2y to the power of 1 plus 0. Good, and now if we evaluate this one at 1 comma negative 2, we end up with a negative 1. Good. Okay, so we have these kind of 4 statements here. Let me erase this. Okay, so we have our two partial derivatives, the derivative with respect to x of this given function, the derivative with respect to y on this same given function, and then for both cases we found or evaluated the derivatives at a specific point. Let's think about what this means. Let's try and interpret this graphically. Okay, so using geogebra.org 3D calculator, here is this 3D grid, right? So the plane that you see is what I often call the floor, right? It's the two-dimensional plane that describes the possible input values. So we were working with the point 2 comma negative 1. So let's graph that point. 1 comma negative 2. 1 comma negative 2 comma 0 is the point we were interested in. So that becomes this point on the domain, right? It's just on this sheet here. Let me gray it out. I think I can. There it is. So this grayed out plane there, you can see. is the domain of our function. This is the point 1 comma negative 2. And now we're going to take that value and we're going to plug it into our function. And I already typed in our function here as f. f of x comma y equals to 2x cubed plus 3 x squared y plus y squared plus 2. So if I evaluate that function at the input values of x equals to 1 and x equals to negative 2, we end up with a point of 2. So we end up with this point here. Let me tilt it so we can see that it's kind of hovering above it. Okay, so the point A is hovering above the point B. You can see it better here, right? So this is, it's got some height now. Now this is in this three-dimensional space. Let's connect them. That looks a little better. Okay, so there's this little line here to show you where it reaches, and it's this point in three-dimensional space again. It's kind of hard to see, right? It's there. And then we can just keep going. We can always just plug in more points into our function. Let's do a couple more. Let's do the point negative 1 and positive 2. So it would be point negative 1 and positive 2. And that leads to some other point up there. Good. So let me tilt this a little bit. There we go. So you see it's some point up there. And then we can do it again. It will be, how about the point positive 0.5 and negative 0.9. Right? Just randomly picking some points. 0.5 and 0.9. 0.9. Boom. That leaves us to some other point. Good. So I'm just coming up with points, right? So at the moment I have 3 points floating in air that are starting to describe my output function. Well, 3 points doesn't really give us much of an idea, but if we kept going and we did more points, hundreds, thousands, millions of points, eventually all those little points would begin to give us this three-dimensional shape. So we can just click it on here and it'll give it to us, and that's what it is. So those 3 points, those little black points are, wait a minute, something's weird. G, something's wrong with G. Oh, this is supposed to be negative 0.9. So input value, okay, good. So all those points, those 3 points, should be on this purple surface, right? That's what generates this 3D image. This F point is right there on the purple surface, and then if we tilt it this way, we can see that G is also on that surface, and that initial point A is also on that surface. If we tilt it this way, we can see the little point on the ground, and then it goes up to a height A, and then it's on the surface. Good? Okay, so now what are we interested in with this surface? I'm going to change the color of the surface. I'm not too happy with it. Color, let's go with a lighter. I think it might look better if it was like a light blue. Oh, well, that's a weird color. Interesting. Sure, let's stick to that one. Okay, a teal looking kind of color. Okay, so now let me get rid of these other points, F and G. They're just kind of crowding things. So let's unclick that one. Click that one. Okay, so we still have point B. So coming over here, we still have point B, which is the input value, and then we plug it in and we get the value A. So we still have this little segment there, leads to point A. And now we're interested in the instantaneous rate of change if you're standing on A, right? So if you're a little stick figure, let me draw on this. Okay, so we have our surface and we have our point right here. Remember that this point right here, then it is the point f of 1 comma negative 2 is equal to the point A. Well, we need an input value, right? So correction, it's a three-dimensional point, so it's point A is equal to 1 for x, negative 2 for y, and then the output value is f of 1 comma negative 2. And I believe that's at this point right here. And so we're interested in figuring out the instantaneous rate of change if you're a person standing on this surface, right? If you're a little stick person, let's put you in blue, a little thicker. If you're a little stick person standing right here, right? And you want to go, well, okay, you're standing right at that point. What is your instantaneous rate of change? Well, obviously, it depends on the direction. If you're going down, looks like it's going down that way. If, on the other hand, you turn around, you could be walking uphill that way. Your instantaneous rate of change would be some positive number if you're walking in that direction. The instantaneous rate of change could be negative if you're walking in that direction. And what if you're just walking this way over here? You could be walking that way, or you can be walking in the opposite direction, right? So the direction in which you go makes a difference when you're trying to answer what's the instantaneous rate of change. So what we're going to do is we're thinking about finding or interpreting f sub x of x comma y. So this means that we want to go in the x-axis direction. In this graph, remember this is x. So toward the positive x-axis direction is this way. So you're standing on this little surface and you gotta turn and face the positive x-axis direction, right? On the floor of this, it would end up being, let's say that this guy, this point here maps to some point down here, and it's the point 2 comma negative 1. No, 1 comma, so x equals to 1. Here's 1, x equals to 1. So it kind of travels down this way. And then y equals to negative 2 is like right there. Y equals negative 2. So these points kind of come in meeting, and then they go up, and then that's where they meet right there. Okay, so in the positive x-axis direction. So what we're going to do is we're going to hold y equals to negative 2 constant. So on the floor, we're going to travel like this. We're going to be traveling left and right along that line, which means that the little stick person is going to be walking from here this way, in that direction. Good. In that direction. As x approaches that way, right? Your instantaneous rate of change in the positive x equals to 1 direction, starting at x equals to 1, going in the positive x-axis direction, means that you're interested in moving this way and you want the instantaneous rate of change at that point. So you want a tangent line that touches this point only one spot, but is parallel to the x-axis and travels in this direction. Let's go back to our graphing calculator. Okay, so along the floor of this, we're going to consider the input values that travel along this line. We want a line where the x is free to be anything, comma, but the y is equal to negative 2. Comma, and the z equals to 0. Okay, so here it is. Let me just tilt it around. So here's the floor. That black line is the floor. The possible input values. We're going to hold the y equals to negative 2 as the constant. So here's y equals to negative 2. And then the x could be anything, so that means it could be anything on that black line. Good. And then as I choose different input values along that black line and evaluate our function, we'll end up with a sequence of values on this surface that look like this. Now let's see. Now we want to hold x, no, x could be anything. Y must be equal to -2. But now we want to graph the points f of x, comma, -2. And let's change the color of that guy. Red. Good. And so now it matches the red from the x-axis. Good. Okay, so let's scoot this around. So as this guy changes, as this value of the inputs along the floor, along the black line, changes and get infinitely close to this point, of course, then its resulting values will travel along this curved red line, which is on the surface, but above or below that black line. Notice that here, we can see that the surface is actually below that plane, so it looks a little bit weird there. But then here it's above the plane, and here it's above the plane. Okay, so we're interested in finding, so you're a little stick person, you're standing right here at A, and now you face the positive x-axis direction, so that means that you face, this black line here, and then you take a tiny incremental little step in that direction. Where are you going? Well, you're gonna go down, right? The tangent line at that point is clearly gonna be some sort of negative slope. So let's find it. Okay, so I'm going to begin by first typing in the equation of the plane, like a sheet of paper, the plane that touches this surface, this teal surface, at just one point, right there, like the tangent plane instead of the tangent line. And it will describe all possible instantaneous rates of changes depending on which direction you want to go in. Okay, so now the equation of that tangent plane is outside the scope of this class. So if you just want to ignore me for a second, that's fine. Otherwise, it's really not that hard to follow. What we want to do is find the derivative of our function with respect to x, which we've already done. Okay, let me write it down actually over here. We already have this information right here. So we want to do the following. We want to take this plane, I don't know, let's call it P, plane with respect to x comma y is going to be equal to f sub x evaluated at 1 comma -2 times x minus 1 plus f prime sub y evaluated at 1 comma -2 y minus -2 plus f of 1 comma -2. Okay, so well, we already have this. This is easy. This can be -6. -6 x minus 1 plus, and this is -1, and that becomes y plus 2. And if we evaluate our function at 1 comma -2, we're going to get a 2 there, so it's plus 2. So there's our plane function is equivalent to this. So let's simplify that a little bit. Plane sub x comma y equals to -6x plus 6 minus y minus 2 plus 2. Okay, those guys are going to cancel, easy. And so we'll end up with the plane is going to be x comma y equals to -6x minus y plus 6. Okay, again, this is not in the scope of our class, so I just kind of quickly went through it. You wouldn't be asked to do this for homework or anything like that, but if you could follow it, it's not that hard. So it is -6x minus y plus 6. And let's go back to our equation over here. And let's type it in. So let's call this a new function, p of x comma y is going to be equal to minus 6x minus y plus 6. Okay, so there it is. That's messy looking. Let's see if we can rotate around. So what we have here is a plane, that dark gray one, it's a plane that within a short neighborhood of the teal, right, at that point, we want to go and touches only at one point. Now it's hard to tell from here because in fact it intersects in other places, but when you're really, really close to the point A, I'm not liking any of these. Okay, well, it's not going to be perfect, but hopefully we get a sense. So at the point A, let's get rid of that guy again. We're interested in a plane that only touches the teal function at A within a certain neighborhood. It can touch it in other places. So if you recall, okay, so when we were back with a two-dimensional graph, we're looking at tangent lines like this. We would say a tangent line touches the function at one point, but that's not really true because you can see clearly that it touches it at another point as well. Here it crosses there. So it's not sufficient to say that a tangent line only touches our function at one point. Sometimes that's true, like if I swing back over this way, now it looks like maybe the function only touches at one point, but actually still that's a lie because eventually this will come down here and this guy will come and they might cross somewhere down there. Or at a point like say here, it's clearly obvious that it touches there and there. So it's not sufficient to just say that it touches at one point. We want to say that within a neighborhood of the domain, right? If we focus on just one small tiny little area near the input value, then in that neighborhood, it only touches it at one point. So similar to over here, we don't want to say that the plane doesn't touch the teal, that only touches the teal at one spot. It only touches the A at one spot as long as we're relatively close to that value. Good, so it'll be this plane that only touches, when you get close enough, it only touches it at one spot. And that's what this is attempting to provide for us. Well, it looks pretty ugly. Maybe if we change the color, it might look a little bit better too. Come on. Okay, so it only touches it at one spot. And so now we can see that if we want the instantaneous rate of change along that curvature, that red curvature, well, the red curvature isn't quite on the black line. They only share one point, the point A, but they're pretty close, right? So we want to find the slope of the line that lives on this plane that touches that point right there, A, and it is parallel to this red line, which in turn is parallel to the x-axis. That was a mouthful. Good. Okay, so I want a tangent line that goes somewhere along this way. Okay, so let's find that one. Okay, so I want all points where the x is free, the y is -2, and now I want all the points that live on that plane, which is defined by the function p, so it'll be the points p, and then it'll be x comma -2. That should do it. And let's change the color of it. Okay, so let's just strip away some of this stuff. There's just so much stuff everywhere. Let's take away that plane P. That's this plane right there. And let's take away that curve, red curve there. There it is. And so we see is exactly what we wanted, a tangent line. This black tangent line. Let me zoom out a little bit more. this black tangent line, as you can see, there it goes. Well, let's take out the line that is on the floor. So the floor, well, that's a better angle for it. Here is the input values, right? As the y equals to -2 is held constant and x is free, but then we want to think about what happens as it approaches this point B, and then we get this output value here on the teal, and we see that along that curvature there's a tangent line which is parallel to the x-axis. Tangent line that is directly above this black line on the floor is this black line up here. And so we can see it's that tangent line, and that is the slope we're after. So if we evaluate f sub x, the derivative of the function with respect to x, and evaluate it at the point 1 comma -2, we got a -6. So -6 is the slope. -6 is this slope here, right? It tells you the instantaneous rate of change in the x-axis direction if you hold y constant at -2. So standing there at A, you hold y equal to -2 constant, and you walk in the x-axis direction, you're going to have an instantaneous rate of change of -6. Whew, that was a lot. Okay, so now we want to do the same thing, but this time we want to go in the y-axis direction. We want to go that way, a line that is tangent to point A, but facing the y-axis direction. So let's make some changes over here. So let's get rid of that guy. Let's get rid of this guy. Okay, so now we want to think about input values where we hold the x constant at 1. The y is going to be free, and then we want to leave it on the floor so we can see the input values. So now let's twist it around this way, and we see that that black line on the plane here, on the, I call it the floor, gives us the domain value, this guy, and then we evaluate it and go up that way. So this time the x value is held constant at a 1, and it's the y that's free to be anything. So anything along this black line is an input value, and we want to think about what happens as the input values get closer and closer to B along that line. Okay, so then we want to think about the plane. It's still the same plane. Let's go back to our plane. P, where'd it go? P, there it is. So here's that same plane, except now we're interested in facing that way, right? Facing the positive y-axis direction. Actually, where's positive? Yeah, positive is that way. So we want to face that way and see what happens. So let's graph that line along the plane. So we want to graph all the points such that the 1 is constant, the y is free, comma, and then we want to graph the points along P of 1 comma y. And so that gives us all of those points there. So let's strip away everything else. It's kind of messy looking. Oh, let's just get rid of the plane. The plane is just messy. There it is. And actually, I shouldn't have gotten rid of these guys. That's good. Okay, so there you can see. Yeah, it's coming right at you like this. This is the tangent line. This one right here is the tangent line. Maybe we should make it a different color. All right, we're gonna go with brown. Okay, so if we get a nice little angle here, you can see. Okay, so we can see point A is on the surface of this teal, and then we see that this brown line is tangent to that point, but parallel to the y-axis, meaning that it's right above this black line, which represented all the possible input values when you held x constant to 1 and allowed y to kind of move around, but we were interested in what happens as the y values get closer and closer and closer to -2. Right, so on the surface, there's like curvatures that are happening, but at this point, the tangent line is this brown line, and then the slope of that line, as we can see in the positive, so going that way is positive y, see -4, -4. So if you're standing on this point and you want to travel along this brown line, you would be going down by some amount, right? That's what that means. And we calculated it. That's what this -1 means. The slope is -1. In the y-axis direction, when you hold x equal to 1 as a constant, and you're interested in the instantaneous rate of change as y equals to -2, then that's what this is. Good. So if you're standing right there at 1, -2, facing the positive y-axis direction, you take one incremental little step, that slope, the instantaneous rate of change, will be -1. That's what that means. Okay. Pretty messy. Hopefully that made a little bit of sense. Okay, so now let's extend this to second order partial derivatives. Just like we learned back when we were doing derivatives in one variable, a derivative of a derivative is a second derivative, right? And then we can take the derivative of a derivative of a derivative, which is a third derivative, and so on and so forth. Well, likewise here, so we have a function written in two independent variables, x, y, and so we can take a first derivative, a first partial derivative with respect to x or y, and then we can go beyond that and take a derivative of the derivative, giving us the second order partial derivatives. So because there are two variables, then there are four possible outcomes, right? You can kind of see this as this little tree thing where we have some function z equal to some f of x comma y, and then we can either take a derivative of z, derivative with respect to x on the function z, or we can take a derivative with respect to x on the function z. And then once we have that as a function, then again we can choose to do the same thing again. Oops. Back over here, I meant to put derivative with respect to y. So we can take a derivative with respect to x on z, or we can take a derivative with respect to y of z, and then these two would give us functions, and then from those we can do, once again, the derivative with respect to x on the function, which was the derivative with respect to x on z, or we can do the derivative with respect to y on the function, which was the result of the derivative with respect to x of z. And same thing over here, we can do the derivative with respect to x on the function that we first got as the derivative with respect to y on z, or we can do the derivative with respect to y on the function that we got that was the derivative with respect to y on z. And that's all pretty messy, so we developed this new notation. Okay, so let's clean this up a little bit. This is the derivative with respect to x on dz dx, dz, or this one is d dy of dz dx, or this one is d dx of the dz dy, or this one is the d dy of the dz over dy. Right, same thing, maybe a little less messy. Okay, well, likewise, this is d dx of, using the notation from before, this is f sub x, right, the derivative of the function with respect to x of x comma y. This is d dy of, this is f sub x of x comma y, right? So d dx of the f sub x, or d dy of the f sub x. This is d dx of the f sub y of x comma y. Finally, this is d dy of the f sub y of x comma y. Okay, they all mean the same thing so far. Maybe I should put like little lanes. I'll do that in a second. Okay, also, this is ugly notation, so often you just see this, ddx of f sub x, kind of dropping out this x comma y, ddy of the f sub x, and ddx of the f sub y, and d sub y of the f sub y. Okay, it's a little bit less messy. And one more variation on this. This is f sub xx, right? This notation indicating this. And then this is going to be f sub xy. And this one is going to be equal to f sub y x. And finally, this last one is f sub y y. And, well, finally, we can also just put these f sub x's in there again. This could be f sub xx of x comma y. This is f sub xy of x comma y. This is f sub y x of x comma y. And finally, f sub y y of x comma y. Whew, notation, right? Notation is part of the challenge in calculus, right? So all these things mean the same thing. And then all of these things mean the same thing, right here in this lane here. And finally, all of these guys mean the same thing, right? So there's 1, 2, 3, 4, 5, like 6 different ways in which you can refer to the same thing for each one of these. So the point, though, is we take the function, which is written in 2 variables, x and y. First, we take a derivative with respect to either x or y, and that leaves us to 2 functions. Let me zoom out a little bit more now. So we start with some function here, which leads us, which is written in 2 independent variables, x and y. We take a derivative with respect to x, and so that leads us to a function, to some function, with x's and y's in there, potentially, but this is a derivative with respect to x. Same thing over here, derivative with respect to y. This leads to some other function, also with x's and y's in here. And then again, we can choose to take the derivative of that function with respect to x or with respect to y. And then same thing here. So we end up with 4 possible outcomes. Good. So these are the 4 possible partial derivatives, second order partial derivatives. Here's a nice little table your author provided. So if z equals to f of x comma y, then here are all those guys over there. Same thing. Pay close attention to this particular order. The derivative of the function, we start taking the derivative with respect to x, and then once we have that function, we later take the derivative with respect to y. So sort of the outside derivative is here, and that matches with that outside derivative, right? So to create this, to find the answer, we start with the derivative of x first, get an answer, and then take the derivative with respect to y. So that would be this one, for example. We take the derivative with respect to x first, and then later we take a derivative with respect to y, and that's what this is. X first, derivative with respect to x first, then y, right? X first, then y. And then the other way around here. First we take the derivative with respect to y, and then with respect to x. So derivative with respect to y first, that's this one, and then with x. Good, so that corresponds to this. First find the derivative with respect to y, and then find the derivative with respect to x. It isn't always going to be the case that these two give you the same result, but for everything we do in this class, it will. So for us in this class, f sub xy is really equal to f sub yx. In all the cases we're going to run into, finding these two things, you can find them separately, but then show that they actually equal each other, right? Taking a function and finding the derivative with respect to x first, then finding the derivative with respect to y of that function is going to give you the same result as finding the derivative with respect to y first and then finding the derivative with respect to x of that resulting function. You'll see that they both end up giving you the same thing. Again, not always, but for us in this class, that will be true. Good. Okay, so let's do one of these. Okay, so here are the exercises for 7.2. Let's see, all of these are asking for the first order partial derivative. Squeezing on over here, here we go. Here we have second order partial derivatives. So for instance, let's do a couple of these. Okay, let's take a look at, say, number 32. It says find the indicated second order partial derivatives for each function. Okay, so number 32, for instance. Number 32 has find f sub yx if the function, so f of xy is given to be negative 2x plus y plus 8. This should be easy. So if we want to find yx, we got to go in this order. So we first find the derivative with respect to y. So this would be d dy of our function f sub xy, which is the same thing as saying find f sub y of x comma y, which is the same thing as saying find the derivative with respect to y on the function negative 2x plus y plus 8. Well, that's easy. This is some constant, that's 0. That's just going to be 1 plus 8. So the answer is just 1. So we found the derivative with respect to y, and now next we want to find the derivative with respect to x. So now f sub yx on x comma y is equal to the derivative with respect to x on f sub y of x comma y, which is equivalent to the derivative with respect to x on this function, which was just 1. And the derivative of any constant is just equal to 0, right? So that's our answer. So f sub yx on x comma y just equals to 0. Okay, well that was kind of boring. Let's try a more fun one. How about 36? 36 seems fun. Let's take a look at 36. So now number 36. We're given that f of x comma y is equal to e to the power of 3x plus 2y. And we're interested in first finding the derivative with respect to y, getting a function, and then finding the derivative with respect to x, right, in that order. So first we got to find the derivative with respect to y on our function f of x comma y, right? So this is the same thing as f sub y of x comma y, which is the same thing as the derivative with respect to y on our function, which is e to the 3x plus 2y. Good. All right, so then this derivative should be easy. This is going to be equal to, copy it. So it'll be e to the power of 3x plus 2y times, the chain rule says now we got to multiply this times the derivative with respect to y of the numerator, which is 3x plus 2y. And the derivative with respect to y on this function is just going to be 2. Good. So this leads me to conclude that f sub y on x comma y is going to be equal to just the number 2 times e to the power of 3x plus 2y. Okay, so I found my f sub y value, but now I got to come back and find the result when we take that function and find the derivative with respect to x now. So I can find my f comma x. Okay, so now we want to find f sub yx of x comma y, which is equal to the derivative with respect to x of the function f sub y of x comma y, which is equivalent to the derivative with respect to x on 2e to the 3x plus 2y, which is going to be equal to 2e to the 3x plus 2y times the derivative with respect to x of the numerator, which is 3x plus 2y by the chain rule. And then this is just going to be equal to 3. So we'll have an extra term of 3. 3 times 2e to the 3x plus 2y. Good, which is just going to be 6. So 6e to the 3x plus 2y will be our answer here. F sub yx of x comma y. Okay, back to our problems. Let's try number 64, which just asks you to find all 4 second-order partial derivatives. Okay, so the instructions are just to find all 4 second-order partial derivatives of this function. So let's just go about and find them all. So first of all, we're going to need the first order. So we're going to need f sub x of x comma y, which is equal to the derivative with respect to x on this function. Right, so remember, just focusing on the x. If this was, if y is just some constant, this is like x squared over 3 or something, then its derivative would simply be 2x the power of 1, and then there's still a y down there, minus, and now the derivative of this guy, remember, this could be rewritten as x to the negative 1, so this becomes negative 1 y squared x to the minus 2, right? Again, thinking about this guy, or this is x squared y to the minus 1 minus y squared x to the minus 1. And so again, if this is just some constant, just leave it alone. Bring down the minus 1 and then subtract 1. So we get our power rule. All right, so then this can just be rewritten as 2x over y plus 1, and this becomes y squared over x squared. Right? Or with negative exponent notation, which might be useful for the next derivative, we can again rewrite it as 2x y to the minus 1 plus y squared x to the minus 2. Right? So then that's that first partial derivative with respect to x. Now let's do the one with respect to y. So f sub y of x comma y is equal to the derivative with respect to y on the function x squared y to the minus 1 power. Come on. I'll write it this way. dy x squared over y minus y squared over x, which then can be thought of, right, it's convenient to think of it this way, x squared y minus 1 minus y squared x to the minus 1. And so the derivative with respect to y, so we bring down the minus 1, subtract 1, so that becomes minus x squared y to the minus 2, and minus 2y to the power of 1 x to the minus 1, which then becomes negative x squared over y to the second power minus 2y over x, right? Either one. Okay, so now that we got both of the first order derivatives, now we got to find the subsequent second order derivatives. Okay, so f sub x of xy is equal to the derivative with respect to x on the function f sub x of y, which gives you the derivative with respect to x on 2x minus, 2x y to the minus 1 plus y squared x to the minus 2, which is then equal to, respect to x, so that would be a 2y to the minus 1 power minus 2y squared x to the minus 3 power. Good. Okay, so then next, the derivative of xy of x comma y is equal to the derivative with respect to y on the function f sub x of x comma y, which is then dy on the function 2x y minus 1 plus y squared x minus 2, which then gives you minus 2x y to the minus 2 plus 2y x to the minus 2, right? So just focusing on the variable y, we use our power rule. Bring down minus 1 gives you negative 2. X is just some constant. Times y to the minus 1 gives you minus 2. Plus, bring down the exponent in front as a factor. We get a 2 to the power of 1. And then this comes along for the ride. It's just some constant. So we found this guy. Good. So now let's find the other ones. So now if you want to find f sub yx on x comma y, that is the derivative with respect to x on the function f sub y of x comma y, which is the derivative with respect to x on the function, and let's use this style of notation here, minus x squared y to the minus 2 minus 2y x to the minus 1 with respect to x. So bringing this 2 out in front gives me minus 2x, the power of 1, and then y to the minus 2, minus 2 times negative 1 y x to the minus 2, which then simplifies to minus 2x y minus 2 plus 2y x to the minus 2. And at this point, we want to point out that we should get the same answer as this one. One is exactly the same answer as that one. Right? So this one is f sub y x on x comma y. Get that one. And then finally, we want to find f sub x, yy, not xx, we already found xx. F sub y of x comma y, which is the derivative with respect to y on the function f sub y of x comma y, which then gives you the derivative with respect to y on the function, and again, let's use this style of notation here. That'll be minus x to the second power, y to the minus second power, minus 2y x to the minus 1 power, which then gives you, with respect to y, so that would be positive 2. Okay, with respect to y, we'll end up with a minus times a minus 2, y to the negative 3, so then there'll be this x squared just hanging out there, y to the minus 3. And then y here was just going to be a 1, so there'd be minus 2x to the minus 1. Right, and 1 because of the y. So then this will just simplify to f sub y of x comma y is equal to 2x squared y to the negative 3 minus 2x to the minus 1. Good. Let me just squeeze it in here in a slightly different way. F sub y of x comma y equals to 2x squared over y to the positive 3 power minus 2 over x. Okay, so that's ugly. Zoom out here and let's highlight all of these. Highlighter. Well, they didn't ask us for this, but we need to find it. Oh, let me label these. This one was also f sub x of x comma y. And although they didn't ask us for it, we have to find the first order derivatives in order to find the second order derivatives. So here is the first order derivative with respect to x. And then here is the first order derivative with respect to y. So we needed that to be our guide to then find the 4 second order derivatives. So here is these guys. Let me erase this and let's rewrite it here. So this is f sub xx of xy equals to 2 divided by y minus 2y squared divided by x cubed. That's this one right here. And this one we can rewrite as f sub xy of x comma y equals to, and as we saw above, this one right here, let me highlight it in green. This one gave us the exact same result that we got up here once we did it in the opposite order. Right? Up here, we got the exact same opposite, so these two are equal to each other. And so I can come back over here and say that this is the same thing as f sub yx of x comma y. Both of them gave us the same answer of minus 2x over y squared plus 2y over x squared. And finally, we have this third one, f sub y of x comma y is equal to 2x squared over y cubed minus 2 over x. Good. So let's box these all up and okay, so given the original function, it's always convenient when you have something written this way to rewrite it like this with negative exponent notation. And then we have our first order partial derivative with respect to x, first order partial derivative with respect to y, and then we use those to then get our second order partial derivatives, and here they are. Okay, so that should be enough to get started with your homework. So hopefully you will be able to do it and not have too many problems. Otherwise, come talk to me with questions.